The James Webb Telescope just captured galaxies that formed 290 million years after the Big Bang. Black holes heavier than entire galaxies. Stars exploding at the edge of time itself. We are seeing light that has traveled for 13 billion years to reach us. You are about to witness discoveries that challenge the very laws of physics. If you are ready to see the cosmos like never before, hit that subscribe button. The journey begins now. "1 million miles from Earth, a machine the size of a tennis court hovers in the darkness. The James Webb Telescope cost $10 billion and took 20 years to build. Its mirror unfolds like origami in space. 6 hexagonal panels made of gold-coated beryllium catch-light that left distant galaxies when the universe was an infant. This telescope does not orbit our planet like Hubble. It circles a point in space where gravitational forces balance perfectly. Scientists call this the second Lagrange point. Here, shielded by a sun shield the size of a tennis court with protection equivalent to sunscreen factor 1 million, Webb stares into the infrared spectrum. Why infrared? Because the universe is expanding. Light from the most distant galaxies stretches as it crosses space. By the time ancient starlight reaches us, wavelengths that started as visible blue and ultraviolet have been pulled into the infrared range. Hubble could never see this. Its visible light cameras went blind at a certain distance. Webb sees what Hubble could not. The telescope launched on Christmas Day 2021. For 6 months, engineers held their breath as it deployed. 1,044 things had to work perfectly. A single failure would doom the entire mission. Every panel unfolded without error. Every instrument activated flawlessly. Then Webb opened its eye and looked deeper into time than any machine in history. Each observation is a time machine. When you see a galaxy 1 billion light years away, you witness that galaxy as it existed 1 billion years ago. The light took that long to travel across space. Webb pushes this principle to its absolute limit. The telescope captures photons that began their journey when the universe was less than 5% of its current age. These ancient galaxies appear as faint red smudges against the cosmic darkness. Their light has been traveling for more than 13 billion years. We are not just seeing distant objects. We are watching the birth of the cosmos itself. Scientists thought they understood what early galaxies should look like. Small, faint, and simple. The universe was too young for anything complex to exist. Webb shattered those expectations in its first week of operation. The galaxies it found were wrong. They were too big, too bright, too mature. Some had already formed massive structures that should have taken billions of years to develop. One astronomer called it completely unanticipated. Another said it might break cosmology. The standard model of the universe predicted one thing. Webb showed something entirely different. Every image revealed galaxies that challenged decades of theory. Every spectrum told a story that did not fit the textbook narrative. What happens when your best instrument shows you the impossible? You keep looking. And what Webb found next was even stranger. The galaxy appeared as a tiny red dot in Webb's first deep field images. Astronomers labeled it with a catalog number and moved on. Then someone ran the numbers. The light from this galaxy had been stretched by a factor of 15. It existed just 290 million years after the Big Bang. The universe is 13.8 billion years old. This galaxy formed when reality was only 2% of its current age. Call it jades. Scientists stared at the data for months. Convinced they had made an error, they rechecked everything. The measurements held firm. This was not a mistake. JWST spans more than 1,600 light-years in diameter. It glows with the light of forming stars. The galaxy is bright enough that Webb could have detected it, even if it were 10 times fainter. That means other galaxies from this era are waiting to be discovered, perhaps galaxies that formed even earlier, in the first 200 million years after creation. Here is the problem. Standard cosmology says galaxies grow slowly. They start as small clumps of matter in dark matter halos. Gravity pulls in gas. Stars ignite. Over billions of years, galaxies merge and grow massive. JWST did not follow this script. The galaxy is too luminous, too organized, and too large for its age. Computer simulations predicted early galaxies would be dim, chaotic, and tiny. JWST is none of these things. It radiates light from young stars, not from a black hole. That makes it even more puzzling. Black holes can produce tremendous brightness from a small region, but star formation requires time that JWST should not have had. Other early galaxies showed the same pattern. They were bigger and brighter than they should be. One astronomer described it as finding a fully grown adult where you expected to see a newborn infant. The universe simply did not have enough time for these structures to form through conventional processes. Some scientists proposed that galaxy formation happened faster in the early universe. Perhaps stars formed more efficiently back then. Maybe dark matter halos collapsed more rapidly. These ideas help, but they do not fully explain the observations. The galaxies are still too extreme. Another explanation involves what astronomers call initial conditions. Perhaps the Big Bang did not spread matter evenly. If certain regions started denser than others, galaxies could have formed faster there. But this raises new questions. Why would those dense regions exist? What process created them? The discovery of JWST extended our view into cosmic history by 40% in just 18 months of observations. Every new galaxy found at these distances adds another piece to a puzzle that refuses to fit together. One researcher admitted that they built these machines not to confirm the paradigm but to break it. They just did not know how it would break. And then Webb found something that made massive galaxies look like a minor problem. In the modern universe, there is a rule. For every 10,000 solar masses of stars in a galaxy, there is roughly one solar mass in the central black hole. This ratio holds everywhere we look. The Milky Way follows it. Nearby galaxies follow it. It is a cosmic law until Webb looked at the early universe. Astronomers found a galaxy from when the cosmos was only 570 million years old. They measured the mass of its stars. Then they measured the black hole at its center. The numbers made no sense. The black hole equaled 10% of all the stellar mass combined. For every 10 solar masses of stars, there was one solar mass of black hole. This galaxy broke the rule by a factor of 1,000. Scientists call it an overmassive black hole. The term barely captures how extreme this is. Imagine if your heart weighed 1/10 as much as your entire body. That is the proportion we are seeing in these early galaxies. The black hole is not just at the center, it dominates the entire system. Webb found dozens of these objects. They appear as little red dots in deep field images. The red color comes from hot gas swirling into the black hole. As matter accelerates toward the event horizon, it heats to millions of degrees and radiates energy. This creates a compact, blazing core that outshines the surrounding stars. The discovery challenges everything astronomers thought they understood about galaxy evolution. In nearby galaxies, the black hole and stars grow together. A bigger galaxy has a bigger black hole, maintaining that 1 to 10,000 ratio. The relationship is so consistent that scientists built entire theories around it. These early galaxies show a completely different pattern. The black holes grew first and grew fast. They became massive before their host galaxies had time to form many stars. One researcher described it as a baby with the heart of a giant. The proportions are all wrong. How did these black holes get so big so quickly? There are two main theories. The first involves stellar collapse. When massive stars die, they can form black holes. These black holes then grow by consuming nearby matter. But this process takes time. Even if a black hole eats constantly at the maximum possible rate, growing from a stellar remnant to millions of solar masses in 500 million years requires nearly perfect conditions. The second theory proposes that some black holes were born big. Instead of forming from collapsing stars, they formed when massive clouds of gas collapsed directly into black holes. These primordial black holes would start with masses of thousands or even millions of solar masses. They bypass the slow stellar formation route entirely. Webb data now supports the direct collapse scenario. Several observations hint that these massive black holes could not have grown from stellar seeds in the time available. They must have started large. This creates its own mystery. What special conditions allow a gas cloud to collapse directly into a black hole instead of forming stars? The story gets stranger still. These overmassive black holes are not randomly scattered across the early universe. The black holes sit in a network. Astronomers mapping the early universe discovered that little red dots cluster together in the cosmic web. This is the large-scale structure of the universe, where galaxies gather along filaments of dark matter like beads on invisible strings. The positioning tells us something critical about when and how these black holes formed. More evolved galaxies appear at the nodes where filaments intersect. Less developed galaxies scatter along the filaments themselves. The little red dots occupy specific locations in this web. They are not the most massive structures, but they are among the most active. Their black holes are consuming matter at ferocious rates. One survey analyzed 7 little red dots from when the universe was 12.5 billion years younger than today. All 7 showed the same pattern: overmassive central black holes in relatively small galaxies. The consistency is striking. This is not a few weird outliers. It appears to be a distinct population of early universe objects. The black holes emit radiation as they feed. This energy pours into the surrounding gas, heating it and pushing it away. Astronomers call this feedback. In nearby galaxies, black hole feedback regulates star formation. Too much feedback and new stars cannot form. Too little and stars form so rapidly that the galaxy runs out of gas. In these early galaxies, the feedback might explain why the galaxies stayed small. The massive black holes turned on early, blasting their surroundings with energy. This prevented the galaxy from forming many stars. The black hole essentially kept its host galaxy stunted. Only later, after the black hole quieted down, could gas cool and form stars at normal rates. This would gradually restore the ratio we see in modern galaxies. But there is a timing problem. If black holes form first and prevent star formation, where did the black holes come from? They need gas to grow. If they are blasting all the gas away with feedback, how did they get massive in the first place? The sequence of events does not quite work. Some researchers propose a burst scenario. The black hole forms and goes through a rapid growth phase, consuming massive amounts of gas before the feedback energy builds up enough to push material away. During this window, the black hole can grow to millions of solar masses. Then the feedback kicks in. shutting down both black hole growth and star formation. Later, the system settles into a calmer state. Others point to mergers. If two galaxies collide, their central black holes can merge. This instantly creates a more massive black hole. Early universe galaxies existed closer together, making mergers more common. A series of mergers could build up supermassive black holes quickly. Webb has already found evidence of merging black holes in the early universe, lending support to this idea. Recent observations add another twist. Some overmassive black holes sit in regions with surprisingly low chemical enrichment. Stars produce heavy elements when they die. These elements enrich the surrounding gas. A galaxy with many stars should show high levels of these elements. But some overmassive black hole hosts show low enrichment, suggesting few stars have lived and died there. This fits the primordial black hole theory. If the black hole formed directly from pristine hydrogen and helium gas, it would not need prior generations of stars. The low chemical enrichment would be expected. But confirming this requires more observations. Each spectrum Webb captures adds detail to the picture. What astronomers know for certain is that the early universe operated differently than the modern one, and the differences go beyond just black holes. 350 years ago, a star exploded. The supernova flash raced outward at the speed of light, crossing the empty space between stars. In 2025, that pulse of radiation reached a cloud of interstellar dust and gas. The James Webb Telescope watched what happened next. The light hit the dust and illuminated it from within. Webb captured the glow in exquisite detail. What scientists saw resembled the knots and walls of wood grain. Tightly packed sheets of material revealed structures on scales of 400 astronomical units. That is less than 1/100th of a light year. This is finer detail than anyone knew existed in the interstellar medium. Astronomers call this phenomenon a light echo. It works like an audio echo bouncing off canyon walls, except with light. The supernova flash acts as a cosmic spotlight, briefly illuminating material that would otherwise remain invisible. As the light pulse expands outward, it progressively lights up more distant material, creating an echo that moves through space. The observations targeted a light echo near the Cassiopeia A supernova remnant. This is the shattered remains of a star that exploded in the 1600s. Webb did not look at the remnant itself. Instead, it focused on background material lit up by the ancient explosion. The material has nothing to do with the star that exploded. It is unrelated interstellar dust and gas that happened to be in the right place at the right time. The fine structure shocked the research team. They expected to see diffuse, formless clouds. Instead, they found organized layers. One scientist described it as an onion with nested shells. The sheets of material stack upon one another in intricate patterns. Some appear influenced by magnetic fields threading through space, aligning the dust into parallel formations. This discovery matters because the space between stars is not empty. Every cubic meter contains atoms of gas and grains of dust. Most of this material clumps together in clouds. These clouds give birth to new stars. Understanding their internal structure helps astronomers grasp how star formation works. Before Webb, scientists could only study the outsides of these clouds. Now they can peer inside. The sheet-like structures measure about 400 astronomical units across. For scale, our entire solar system, including the orbit of Neptune, spans only 120 astronomical units. These sheets are several times larger than our planetary system. yet they are just small features within much larger clouds. Why does the material organize into sheets rather than random blobs? Magnetic fields provide one explanation. The interstellar medium is threaded with magnetic field lines. Charged particles and dust grains tend to align along these fields. Over time, this creates elongated structures. Turbulence in the gas also plays a role, stirring the material into complex patterns. The researchers believe that most dense, dusty regions in space look like this on the inside. We have just never been able to look inside them before. Every molecular cloud, every star-forming region, probably contains similar layered structures. Webb has given us a template for understanding the three-dimensional architecture of interstellar space. These observations also reveal how matter moves between stars. The sheets might channel gas flows, guiding material along specific paths. Where sheets intersect or compress, conditions might favor star formation. Understanding this helps predict where new stars will ignite. The light echo technique opens a new way to study the interstellar medium. Astronomers can wait for supernovae or other bright transient events to illuminate different regions of space, then observe the revealed structures with Webb. Each echo provides a snapshot of a different volume of interstellar space. But while Webb was studying the space between stars in our region, it was simultaneously looking at stars dying in the most distant reaches of time. On March 14, 2025, a space telescope detected a flash of gamma rays. The burst lasted several seconds. Within hours, ground-based telescopes around the world swiveled to observe the fading glow. The light revealed something extraordinary. This explosion happened when the universe was only 730 million years old. The burst originated from a massive star at the moment of its death. Stars more than 10 times heavier than our home star live fast and die violently. When their nuclear fuel runs out, the core collapses in less than a second. The outer layers crash inward, rebound off the collapsing core, and explode outward. This is a supernova. In the most massive stars, the collapse also generates jets of material that punch through the star at nearly the speed of light. These jets produce gamma rays, the highest energy form of light. When one of these jets points toward Earth, we detect a gamma ray burst. This is exactly what happened on that March morning. Astronomers had seen distant gamma ray bursts before, but this one set a record. The light had been traveling for more than 13 billion years. We were watching a star explode during the epoch of reionization, when the first stars and galaxies were clearing the fog of neutral hydrogen that filled the early universe. The discovery was not accidental. Ground-based telescopes confirmed the extreme distance using spectroscopy, but the crucial observations came 110 days after the burst, when Webb turned its attention to the region. By then, the initial flash had faded. What remained was the supernova itself, a slower and dimmer event than the gamma-ray burst. Webb separated the fading light of the supernova from the much dimmer glow of its host galaxy. This is technically challenging. The supernova outshines its host by a significant factor, and both appear as a single point of light from Earth. Webb's sharp infrared vision made the separation possible. The telescope identified both the explosion and the galaxy that hosted the dying star. The observations revealed something unexpected. This ancient supernova looked remarkably similar to supernovae in the modern universe. Astronomers compared it to a well-studied nearby supernova from 1998. The brightness, the spectrum, and the evolution over time matched closely. Despite occurring in a vastly different environment, the explosion followed the same basic physics. This is both comforting and puzzling. Comforting because it suggests that the laws of physics have not changed over cosmic time. The way massive stars die today is the same as how they died billions of years ago. Puzzling because the early universe had very different conditions. Stars back then formed from nearly pure hydrogen and helium. Modern stars contain heavier elements created by previous generations of stars. These heavy elements affect how stars live and die. The similarity between ancient and modern supernovae suggests that metallicity, the amount of heavy elements in a star, might matter less than astronomers thought. Or perhaps the most massive stars behave similarly regardless of their composition. More observations of distant supernovae will help resolve this question. The host galaxy itself provides clues about the early universe. It is small and faint, barely detectable even with Webb. This tells us that massive stars were forming and dying in some of the smallest galaxies. These galaxies might have been building blocks that merged to form larger structures over time. Finding supernovae this distant also opens a new way to study the early universe. Each explosion acts as a beacon, illuminating its surroundings for a brief period. Astronomers can study the gas around the dying star, measuring its composition and density. This reveals conditions in the interstellar medium billions of years ago. Gamma-ray bursts paired with supernovae also test models of stellar evolution. Theorists predict how massive stars should behave at different cosmic epochs. Observations either confirm or challenge these predictions. The close match between this ancient supernova and modern ones supports current stellar evolution models, but raises questions about why metal-poor environments do not produce more significant differences. Yet even as this star was exploding in isolation, elsewhere in the early universe, black holes were not dying alone. The galaxy had two bright cores. Astronomers noticed this immediately when they examined Webb images of a system called ZS7. The galaxy existed 740 million years after the Big Bang. At first, scientists wondered if they were seeing a single galaxy with unusual structure. Then they analyzed the spectrum. The data showed fast-moving gas near both bright points. The gas moved at velocities of hundreds of kilometers per second, swirling in tight orbits. This is the signature of matter falling into a black hole. The gas heats up as it accelerates, reaching millions of degrees. It emits characteristic wavelengths of light that reveal the presence of an actively feeding black hole. Both cores showed this signature. ZS7 contained two supermassive black holes orbiting each other. This is the earliest black hole merger ever detected. The two objects are spiraling inward, destined to collide and combine into a single, more massive black hole. Webb's sharp imaging allowed the team to spatially separate the two black holes. They are close together but distinct. Ground-based telescopes would see them as a single blurred point. Space-based telescopes before Webb lacked the infrared sensitivity to study such distant objects in detail. Only Webb could resolve this system and identify it as a merger in progress. The discovery has profound implications for understanding how supermassive black holes grow. In the local universe, most large galaxies contain a central supermassive black hole. But how did these objects grow to millions or billions of solar masses? One mechanism is merging. When two galaxies collide, their central black holes eventually sink to the center of the merged system and combine. If mergers were rare in the early universe, black holes would have to grow primarily by consuming gas. This is a slow process. Even eating at the maximum possible rate, a stellar mass black hole takes hundreds of millions of years to reach supermassive scales. Finding mergers at cosmic dawn suggests they happened frequently enough to accelerate black hole growth significantly. The two black holes in ZS7 are not yet touching. They orbit each other, gradually losing energy and spiraling closer. This energy loss happens through gravitational waves, ripples in space-time predicted by Einstein. As the black holes circle each other, they emit these waves, carrying away orbital energy. This causes the orbit to shrink. When the black holes finally merge, the collision will release a tremendous burst of gravitational waves. Future gravitational wave detectors will be able to detect mergers like this one. Current detectors on Earth are sensitive to smaller black holes merging in the nearby universe. The next generation of space-based detectors will extend the reach to supermassive black holes at high redshift. Detecting gravitational waves from early universe black hole mergers will reveal the rate at which these events occurred. Astronomers can then calculate how much of the black hole mass growth came from mergers versus gas accretion. This will constrain models of black hole formation and evolution in the first billion years after the Big Bang. The ZS7 system also tells us about galaxy mergers in the early universe. When galaxies collide, their stars, gas, and dark matter interact. Stars rarely collide directly because space between them is vast. But gas clouds crash together, triggering bursts of star formation. The collision compresses the gas, making it dense enough to form new stars. Eventually, the two galaxies merge completely, forming a single, more massive galaxy. The central black holes take longer to merge because they must lose angular momentum to reach the center. Gas and stars carry away this momentum through gravitational interactions. The black holes spiral inward over millions of years before finally coalescing. The stellar mass of ZS7 resembles the Large Magellanic Cloud, a small galaxy orbiting the Milky Way. Imagine if the Large Magellanic Cloud contained two supermassive black holes as large as the one in the Milky Way center. The black holes would dominate the dynamics of the entire galaxy. This is what we see in ZS7. Finding this merger so early in cosmic history suggests that the processes shaping galaxies and black holes today were already operating back then. But something else about these early systems continued to baffle scientists. Light from the most distant galaxies has been traveling for so long that the universe has expanded significantly during the journey. This expansion stretches the light. Astronomers measure this stretching using redshift, a number that indicates how much the wavelength has increased. A redshift of 1 means wavelengths have doubled. A redshift of 2 means they have tripled. JWST has a redshift of 14.32. The light from this galaxy has been stretched by a factor of 15. Ultraviolet light that left the galaxy has arrived at Webb as infrared. This is why infrared telescopes are essential for studying the early universe. The light has shifted so far toward the red end of the spectrum that visible light telescopes cannot see it. Measuring redshift requires spectroscopy. Webb splits incoming light into its component wavelengths, creating a spectrum. Certain elements in the galaxy produce emission or absorption lines at specific wavelengths. Scientists know what these wavelengths should be when the light is emitted. By measuring where the lines appear in the observed spectrum, they can calculate how much the light has been stretched. For JWST, hydrogen emission lines that should appear in the ultraviolet are observed in the infrared. The shift is so large that there is no ambiguity. This galaxy is genuinely ancient. The light we see left the galaxy 290 million years after the Big Bang. Since then, it has been traveling through expanding space for more than 13 billion years. The expansion of the universe also affects how we perceive distance. When astronomers say a galaxy is 13.5 billion light-years away, they are describing the light travel distance. But space has been expanding during those 13.5 billion years. If you could freeze the expansion right now and measure the distance to that galaxy, it would be farther than 13.5 billion light-years. Much farther. This co-moving distance accounts for the expansion that has occurred since the light began its journey. Redshift offers a more fundamental measurement than distance. It directly tells us how much the universe has expanded since the light was emitted. A redshift of 14 means the universe has grown by a factor of 15 since that light left its source. The wavelength of every photon has stretched by the same factor. This stretching affects more than just color. It also dims the light. Photons arrive at Earth with less energy than they had when emitted. Each photon is redshifted to a longer wavelength and lower energy. Additionally, photons arrive more slowly because the path they travel through space has expanded. Both effects combine to make distant objects appear much fainter than they would be at close range. Webb compensates for this dimming. With its enormous mirror and sensitive detectors, the mirror collects as much light as possible. The detectors are cooled to a few degrees above absolute zero, reducing noise and allowing them to detect extremely faint signals. Even so, observing the most distant galaxies requires hours of exposure time. The JWST deep field observations totaled more than 70 hours of telescope time. This is an enormous investment for a facility where every hour is precious. Astronomers must justify such long observations by showing that the science return is worth the cost. Discovering the most distant known galaxy certainly qualifies. The redshift record keeps advancing. Before JWST, the most distant known galaxy had a redshift of 13.2. JWST pushed the record to 14.32. More distant galaxies likely exist, waiting to be discovered. Webb can detect galaxies with redshifts up to 20 if they are bright enough. This corresponds to galaxies forming in the first 200 million years after the Big Bang. Finding such galaxies is difficult. They are rare and extremely faint. Astronomers must observe large areas of sky with very long exposure times. Then they must painstakingly analyze the data, identifying candidates and following up with spectroscopy to confirm distances. Each new record holder represents months or years of work. But the effort reveals fundamental truths about cosmic dawn. The first galaxies were not hiding in the distant darkness. They were bright, active, and surprisingly mature, and the universe they inhabited was expanding in a way that still confuses scientists today. Astronomers measure the expansion rate of the universe using a number called the Hubble constant. It tells you how fast galaxies are moving away from each other per unit of distance. The current value is around 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, a galaxy recedes 70 kilometers per second faster. A megaparsec equals about 3.3 million light-years. So, a galaxy 3.3 million light-years away recedes at 70 kilometers per second. A galaxy 6.6 million light-years away recedes at 140 kilometers per second. The pattern continues linearly with distance. There are two main ways to measure the Hubble constant. The first uses light from the cosmic microwave background. This is radiation left over from the Big Bang itself, now stretched into microwave wavelengths. The pattern of fluctuations in this radiation tells us the composition and geometry of the early universe. From this, cosmologists can calculate how fast the universe should be expanding today. They get a value of 67.4 kilometers per second per megaparsec. The second method uses nearby galaxies with supernovae. Certain types of stellar explosions have predictable brightness. By measuring how bright they appear, astronomers can calculate their distance. Combining distance measurements with velocity measurements gives the Hubble constant directly. This method yields a value of around 73 kilometers per second per megaparsec. These two values do not agree. The difference is small in absolute terms, but large enough to be highly significant. It persists despite decades of refinement to both methods. This disagreement is the Hubble tension. When Webb began operations, some scientists hoped it would resolve the tension. Perhaps one method contained a subtle error that better observations would reveal. Webb has now collected the largest dataset yet on nearby supernovae. The result confirms the Hubble Space Telescope measurements. The local universe is expanding at 73 kilometers per second per megaparsec. The tension is real. What could explain this discrepancy? One possibility is that our understanding of the early universe is incomplete. The cosmic microwave background measurements assume a specific cosmological model. If that model is wrong, the predicted expansion rate would also be wrong. Perhaps dark energy behaves differently than assumed. Perhaps there is an unknown component of the universe affecting the expansion. Another possibility involves the local universe. Maybe the region of space we inhabit is somehow unusual, expanding faster than the average. We might live in a cosmic void, a large underdense region where the expansion rate differs from the global average. But measurements of our local environment suggest we are in a fairly typical region. A third possibility is that the universe changed its behavior over time. The cosmic microwave background shows us the universe as it was 380,000 years after the Big Bang. Supernova measurements show us the universe over the last few billion years. If something happened in between to accelerate the expansion, it would explain the discrepancy. Some theorists propose new physics. Perhaps gravity behaves differently on cosmological scales than we think. Perhaps dark energy is not constant, but has been growing stronger over time. These ideas require modifying general relativity, Einstein's theory of gravity. Scientists are reluctant to take such a step without compelling evidence. Recent observations with Webb have eliminated one possible explanation. Some researchers suggested that the Hubble Space Telescope measurements were systematically biased by an instrumental error. Webb uses completely different instruments and observing techniques. The fact that it gets the same answer as Hubble rules out instrumental bias as the cause of the tension. This leaves us with a genuine mystery. Two rigorous methods, both refined over decades, give different answers for how fast the universe is expanding. One of them must be wrong, or something about the universe is more complicated than current models allow. Either way, resolving the tension will likely require new physics, and the mysteries extend beyond just the expansion rate. The first stars in the universe were different from anything that exists today. They formed from pristine gas, untouched by previous generations of stars. Just hydrogen, helium, and trace amounts of lithium created in the Big Bang. No carbon, no oxygen, no iron, nothing heavier than lithium. Astronomers call these population 3 stars. They have never been directly observed. Every star we have studied contains at least some heavy elements. But theory demands that population 3 stars must have existed. Someone had to make the first heavy elements. Those elements came from the first generation of stars. These primordial stars would have been massive. Without heavy elements to help cool the gas, star-forming clouds remained hot. Hot gas resists gravitational collapse. Only the most massive clouds could overcome this resistance and form stars. Simulations suggest population. 3 stars typically weighed 50 to 500 times more than our home star. Massive stars burn bright and die young. A star 100 times heavier than our star exhausts its fuel in just a few million years. It then explodes as a supernova, scattering its chemically enriched material into space. The next generation of stars forms from this enriched gas, containing the heavy elements forged in the first stars. Population. 3 stars should have disappeared billions of years ago. They lived too briefly to survive to the present day, but we might still see them if we look far enough back in time. Webb can observe galaxies from when the universe was less than 500 million years old. This is early enough that some population 3 stars might still be shining. Finding them is extraordinarily difficult. A single massive star is too faint to see across billions of light years. Astronomers must look for the signature of many population 3 stars together. The spectrum of pure hydrogen and helium stars differs from metal-enriched stars. Certain emission lines should be strong, others weak or absent. Webb observations of a galaxy called GNZ 11 show tantalizing hints. This galaxy existed 430 million years after the Big Bang. Spectra from the outer regions show strong hydrogen emission with peculiar ratios between different lines. The pattern matches what theorists predict for regions where population 3 stars are forming. The evidence is not definitive. Other processes could produce similar spectral features, but the possibility excites astronomers. If confirmed, this would be the first detection of the stars that brought light to the universe. These objects seeded the cosmos with the first heavy elements, making planets and eventually life possible. Population. 3 stars also influenced the reionization of the universe. After the Big Bang, the universe was hot and ionized. As it expanded and cooled, electrons and protons combined to form neutral hydrogen atoms. The universe became transparent but dark, filled with neutral gas that absorbed most wavelengths of light. This is called the cosmic dark ages. When the first stars ignited, their ultraviolet radiation ionized the hydrogen around them, creating bubbles of ionized gas. As more stars formed, these bubbles grew and merged. Eventually, the entire universe became ionized again. This epoch of reionization represents one of the major phase transitions in cosmic history. Population. 3 stars likely played a crucial role in reionization. Their intense ultraviolet output would have ionized large volumes of space. Early galaxies packed with these stars would have been reionization powerhouses, clearing the neutral fog and allowing light to travel freely through space. Webb is hunting for these objects systematically. Large survey programs are imaging and obtaining spectra of hundreds of early galaxies. Each spectrum might contain the telltale signs of population, 3 stars. Even if only a small fraction of early galaxies still host these primordial stars, the surveys should find them. The discovery would connect us directly to the first chapter of cosmic history. We would see the ancestors of all stars, the original engines that transformed the universe from darkness to light. But while scientists search for the first stars, they have stumbled upon objects they cannot explain at all. They appear as tiny crimson points in Webb's deep field images, compact, bright, red. Astronomers call them little red dots, a deliberately vague name for objects that defy classification. They exist in the early universe at redshifts between 5 and 8. That corresponds to when the cosmos was between 1 and 2 billion years old. The red color comes from hot gas around a central black hole. As matter spirals inward, friction heats it to millions of degrees. This creates an accretion disk that glows across the electromagnetic spectrum. The specific color we see depends on the temperature of the gas and how much dust surrounds the system. Heavy dust obscures shorter wavelengths, making the object appear red. Little red dots are not rare. Large surveys have found dozens of them. They make up several percent of the galaxy population at these early epochs. This abundance surprises scientists. Nobody predicted that so many compact red objects would exist in the early universe. What makes them confusing is their spectrum. When astronomers split the light into wavelengths, the pattern shows both broad emission lines characteristic of black holes and narrower features associated with star formation. The broad lines indicate gas moving at thousands of kilometers per second near a black hole. The narrow lines indicate gas moving much more slowly in star-forming regions. Normally, these two signatures come from different types of objects. Active galactic nuclei, powered by supermassive black holes, show broad emission lines. Star-forming galaxies show narrow lines. Little red dots show both simultaneously. Are they galaxies with unusually active black holes? Or black holes with unusually strong star formation around them? Or something else entirely? The compact size adds to the mystery. These objects appear point-like even to Webb. Their emission comes from a region smaller than about 1,000 light-years across. For comparison, the Milky Way spans 100,000 light-years. Little red dots pack tremendous energy output into a volume 100 times smaller than a typical galaxy. Some researchers argue that little red dots are just heavily dust-obscured quasars. Quasars are the most luminous objects in the universe, powered by matter falling into supermassive black holes. If you surround a quasar with enough dust, the visible and ultraviolet light gets absorbed and re-radiated as infrared. This makes the object appear red and compact. Others suggest that little red dots represent a brief transitional phase in galaxy evolution. Perhaps they are galaxies in the process of forming their first supermassive black hole. The black hole has just turned on and is rapidly consuming gas. This creates the active nucleus signature. Meanwhile, the host galaxy continues forming stars, producing the narrow emission lines. Eventually, the black hole grows large enough that its feedback energy suppresses star formation, and the object evolves into a typical quasar. A third possibility involves the environment. Little red dots cluster together in the cosmic web, sitting at specific locations in the large-scale structure. Perhaps their formation requires special conditions found only in these dense regions. Collisions between gas clouds or interactions between multiple small galaxies might trigger both black hole growth and star formation simultaneously. Webb observations are testing these ideas. By obtaining detailed spectra of many little red dots, astronomers can measure properties like the black hole mass, the star formation rate, the amount of dust, and the chemical composition. These measurements distinguish between different formation scenarios. One recent analysis examined 7 little red dots from the same cosmic epoch. All 7 showed signs of overmassive black holes, with black hole mass equaling around 10% of the stellar mass. This consistency suggests we are seeing a real population with shared characteristics, not just random oddballs. The existence of so many little red dots also constrains models of black hole formation. If these objects are common in the early universe, then the processes creating them must be robust and efficient. This might favor scenarios where black holes form rapidly through direct collapse or accelerated accretion. Another puzzle involves the host galaxies themselves. When Webb images the regions around little red dots with extreme sensitivity, it sometimes detects faint extended emission. This shows that the compact red core sits within a larger, dimmer galaxy. The galaxy is so faint compared to the active nucleus that it almost disappears. Understanding the relationship between the dim galaxy and the brilliant core will reveal how black holes and their hosts co-evolve. Little red dots represent one of the biggest surprises from Webb's first few years. Nobody anticipated finding so many of these enigmatic objects. Each new observation adds pieces to the puzzle, but the complete picture remains elusive. And while little red dots confuse scientists on small scales, the large-scale structure of the universe presents its own challenges. The universe is not uniform. Matter clumps together under gravity, forming a vast network called the cosmic web. Galaxies gather along filaments of dark matter, creating chains of light stretching across hundreds of millions of light years. Where filaments intersect, massive galaxy clusters form. Between the filaments lie voids, vast, underdense regions containing few galaxies. This structure emerged from tiny fluctuations in density present just after the Big Bang. Regions slightly denser than average attracted more matter through gravity. Over billions of years, these small variations grew into the web we see today. Tracing the web back in time reveals how structure in the universe evolved from smooth beginnings to the lumpy distribution we observe. Webb sees this structure at unprecedented distances. By mapping galaxies in the early universe, astronomers can reconstruct what the cosmic web looked like when reality was less than 2 billion years old. The web already existed back then, though in a less developed form. Filaments were shorter and less defined. Clusters were just beginning to form. One recent survey examined a specific patch of sky in extreme detail. The team identified thousands of galaxies at various distances. By measuring their redshifts, astronomers placed each galaxy at its correct position in three-dimensional space. This created a map showing how galaxies distributed themselves at different cosmic epochs. The map reveals that the cosmic web has been in place for most of cosmic history. Even at redshift 8, when the universe was less than 1 billion years old, galaxies clearly cluster along filaments. The basic architecture was already established. What changed over time was the thickness of the filaments and the mass of the clusters at the nodes. Understanding this evolution helps constrain cosmological models. The rate at which structure grows depends on the amount and properties of dark matter and dark energy. Too little dark matter and structure forms too slowly. Too much, and it forms too quickly. The observed evolution of the cosmic web provides a crucial test. Dark matter makes up about 85% of all matter in the universe. It does not emit, absorb, or reflect light. We detect it only through its gravitational effects. Dark matter forms the skeleton of the cosmic web. Galaxies form where dark matter is densest, tracing the underlying dark matter distribution. Webb cannot see dark matter directly, but by mapping visible galaxies, it maps the dark matter indirectly. Galaxies are biased tracers of the dark matter distribution. They preferentially form in the most massive dark matter halos. By studying how galaxies cluster, astronomers learn about the dark matter structure that shaped their formation. Simulations predict the detailed structure of the cosmic web based on our understanding of dark matter and gravity. These simulations start with initial conditions matching the early universe and evolve forward in time. The results can be compared directly to observations. When simulations match observations, it confirms our models. When they disagree, it suggests missing physics. Recent comparisons between Webb observations and simulations show good agreement on large scales. The overall distribution of galaxies matches predictions, but on smaller scales, discrepancies appear. Simulations predict more small galaxies than observed in some regions and fewer in others. This might indicate that galaxy formation is more complex than current models allow. The cosmic web also affects galaxy properties. Galaxies in dense regions evolve differently than galaxies in underdense regions. Dense environments have more frequent galaxy interactions and mergers. These collisions trigger star formation and funnel gas into central black holes. Galaxies in voids experience fewer interactions and evolve more quietly. Webb observations show that little red dots preferentially occupy specific locations in the cosmic web. They are not found everywhere, but cluster in moderately dense regions along filaments. This environmental dependence provides clues about what triggers their formation. Perhaps the combination of sufficient gas supply and frequent interactions creates the conditions for rapid black hole growth. Mapping the cosmic web at different epochs also tracks how matter flows through the universe. Gas streams along filaments toward galaxy clusters, feeding star formation in galaxies along the way. When gas reaches a cluster, it can be heated to high temperatures by shocks and turbulence, shutting down star formation. Webb can observe these processes in action by studying galaxies at different positions in the web. The large-scale structure connects the smallest and largest scales in the universe. The properties of individual galaxies depend on their location in the web. The evolution of the web depends on the cosmological parameters governing the universe as a whole. By studying structure formation, astronomers probe fundamental physics. Yet, even as the web itself takes recognizable form early on, the galaxies within it behave strangely. In the nearby universe, galaxies have a typical density. If you count the total mass of stars and divide by the volume the galaxy occupies, you get a number. For most galaxies, that number falls within a certain range. Early universe galaxies break this pattern completely. Measurements show that high redshift galaxies are much denser than local galaxies. Some are 1,000 times denser. This means they pack the same mass of stars into a volume 1,000 times smaller. The stars in these galaxies orbit in tight, crowded regions where stellar encounters might be common. This creates a paradox. If galaxies start small and dense, then grow large and diffuse, something must puff them up over time. Galaxies need to expand without gaining much mass. This is the opposite of what most theories predicted. Simulations generally show galaxies gaining mass through mergers and star formation, not inflating like balloons. One explanation involves mergers. When two galaxies collide, their stars do not actually collide. Stars are so small and far apart that they pass through each other during a galactic merger. But the gravitational interactions redistribute the stars. The merged galaxy ends up larger and less dense than either parent galaxy. Repeated mergers over billions of years could gradually decrease the average galaxy density. Another factor is the dark matter halo. Every galaxy sits at the center of a massive dark matter halo that extends far beyond the visible stars. As the halo grows through mergers and accretion, the distribution of dark matter changes. This alters the gravitational potential, which can cause stars to migrate outward. The galaxy expands to fill a larger volume even if no new stars form. Feedback from supernovae and black holes also plays a role. Energetic winds driven by exploding stars or active galactic nuclei can push gas out of the galaxy. This removes mass from the central regions, decreasing the gravitational pull. Stars then move to larger orbits, decreasing the overall density. This process, called galaxy-scale winds, is observed in many systems. Some researchers question whether the high densities are real. They point out that measuring the size of a distant galaxy is difficult. The galaxy appears as a small smudge in images. Determining where the galaxy ends and the background begins involves assumptions about the galaxy's light profile. Different assumptions give different sizes. Webb's superior resolution helps address this concern. It can resolve features in distant galaxies that Hubble could not. Measurements with Webb confirm that early galaxies are indeed more compact than expected. The effect is real, though the exact density difference depends on how you define the galaxy boundary. The density evolution also connects to the star formation history. If galaxies form most of their stars early and then stop, they will grow primarily through mergers without forming many new stars. This would maintain their mass while increasing their size, decreasing density. Webb observations show that many early galaxies have high star formation rates, so this scenario does not apply universally. Another consideration involves the role of gas. Galaxies in the early universe contain a higher fraction of gas relative to stars compared to local galaxies. Gas is more compressible than stars. A gas-rich galaxy can be denser because the gas occupies less volume. As the galaxy ages and converts gas into stars, the stellar component dominates. Stars, once formed, do not compress further.